So our next talk will be on iPET, which will be given by Kanav Sabharwal, who is from NUS. So, yeah.
Hi, everyone. So today I'll be presenting iPET, which is a traffic obfuscation scheme to secure IoT communications. This work is a joint collaboration with my colleagues Akshay and Dr. Prasanna under the guidance of Prof. JLN and Dr. Dinil. To motivate our problem, we consider the use case of smart homes, where we see more and more IoT devices being deployed. These devices face the risk of being identified by when they are active and communicating over the internet. They face the risk of being identified by any adversary that has access to monitoring the network traffic. Some of the news articles that we show here highlight this major privacy concern. Some of the user polls showing that more than 50% of the people are still not comfortable deploying these smart devices because of the fear of the privacy concerns they come with, while other studies have shown that the currently available solutions are not enough to circumvent such attacks. To demonstrate this attack, we look at a smart camera which detects some activity in the smart home, and it has to send this message and the live stream over the internet to the IoT server. And we consider an adversary over the internet has access to one of the ISP routers. They can analyze the traffic to identify the device down to the level of the exact make and model of the device. We give more details about this attack, but before that, I highlight the goal, which is defending against such device fingerprinting attacks, as we call them. Yeah. So going ahead, I'll talk about the threat model first. We already talked about the smart home network, where the smart device is deployed, and we consider that the wireless link and both the IoT gateway at the smart home are secure, and so is the IoT server that the device is talking to. The internet link between the two remains vulnerable. And the attacker capabilities, as we already talked about, is to control and compromise the on-path network devices. They can passively sniff network traffic in both directions, and they can monitor the traffic features. Most of the attacks are based on machine learning in this domain, where the attacker, as we just saw, can extract network traffic features, train a machine learning classifier, and then launch the attack to predict the device make and model. We talk a bit more about the kind of features that are used for these attacks. And the first class of features are protocol-specific features, which are available even in the encrypted traffic on the packet headers. So some of the very useful features can be the list and the number of protocols that were used in a communication, the number of DNS queries that were made. The second class of features would be aggregate-based features, which is the traffic volume that was exchanged. Basically, over a few minutes, how many packets were exchanged, what were the length statistics of those packets. And finally, the most recent and the state-of-the-art features include time series. So the network packets are modeled as a time series to map the temporal relationship between different packets. And this is at the granularity of a few microseconds to a seconds, which makes it most robust to obfuscation schemes. So as we discussed, broadly, they rely on protocol-specific features, traffic volume, and the traffic rate. So the defense goal is naturally circumventing these attacks, and the protocol-specific features are easily taken care of as soon as a user deploys a VPN or a Tor network, because the header features are no more available for the adversary. However, the traffic rate and volume are still more than enough to identify the devices with near perfect accuracy. On this front, there are traffic obfuscation schemes that try to add noise to the traffic by padding the legitimate packets or adding dummy packets to the network. And some of them include padding each packet to the maximum transmissible unit size, padding the entire traffic to either a constant or a random rate. And we try to demonstrate these obfuscation schemes. So taking the same example as earlier, the smart camera is forwarding some packets to the IoT server. And once you have a noise model, the noise model will not just modify the legitimate packets, it will add some more packets, which actually leads to a bandwidth overhead. You have more and more packets being forwarded over the link. And We try to summarize this on a trade-off between the bandwidth overhead that you expend for a defense to the attack success for any attacker. And we see for the current approaches, there are two broad cases. There is one case where you are very successful as a defense. The attack success remains low. However, the bandwidth overhead is extremely high. The second case of works that try to reduce the bandwidth overhead, we see that with the latest attacks, they are still vulnerable to a good enough accuracy for an attacker trying to launch an attack. So our goal is to be efficient not just in terms of the bandwidth overhead, but also reduce the attack accuracy for any attacker, or in other words, have the best possible defense at the least possible bandwidth overhead. So the key idea is to use less noise but smarter noise, which most of you would be familiar with adversarial noise. So we use an adversarial noise generator rather than the noise models that have been used till now. And giving a brief background on adversarial perturbations, most of you would have seen this example of a panda image that is used to explain adversarial perturbations. The image is classified correctly by an image classification model. However, on addition of a very small magnitude of adversarial perturbations, the image still looks pretty similar to the human eyes, but now to the machine learning model, it's very confident about in a wrong class. So it misclassifies with a very high confidence. So some of the key features of our interest of adversarial perturbations are they are low in magnitude, they have a high fooling ratio, and some of the latest adversarial perturbations have been shown to be very generic across different models as well. For us, this translates to a low bandwidth overhead, a low attack success, and generalizability between different attack models when we translate the adversarial perturbations, design them for a traffic perturbation scheme. So we discuss our proposal iPET, which is a generative adversarial traffic perturbation scheme. And I'll first take you through the first stage of our defense, which is an iPET basic generator. So the generator transforms some random input into perturbation vector, which is the dummy packet. And these dummy packets, when added to the original traffic, gives the perturbed traffic as that will go from the egress of the home network. We pass these perturbed features to a pre-trained device classification model. So this model is not being trained in this setup, a very similar structure as a GAN. And this model is basically just giving feedback for training our generator. And we use a negative cross entropy loss function, which means the generator is trained to minimize the attack accuracy or minimize the accuracy of the discriminator here. We consider a deployment scenario where iPET basic is deployed by a user to perturb the outgoing traffic from the egress of their home network. However, we consider that nothing stops the attacker from getting access to another instance of iPET. So to be clear, each user gets a specific instance of this generator. So we call this one iPET basic user. And the adversary can also be a part of the defense network. They can access another instance of iPET basic generator, which we call iPET basic adversary. They can extract the perturbed features, passing the traffic through the perturbation mechanism, and retrain their attack model. So when we analyze this, we notice that while an attacker who is agnostic of the defense scheme is not able to identify devices with an F1 score of more than 8%, the retrained attacker that we just considered is still pretty successful. So our job is not done here. And the reason is that we need to increase the stochasticity between different instances that are provided to different users. And when we try to analyze what causes this stochasticity, we realize that the random model weight initialization and the untargeted adversarial training objective that we use is in our favor. However, we are still training against the same attack model. So we are still trying to defeat the same decision boundaries. With this observation, we move forward with the second and the final phase of our proposal, which is iPET Advanced. So this figure just briefly summarizes the training of iPET Basic, where you use a discriminator or an attack model to train a generative model, which we use as iPET Basic. And this solution is extended by mimicking the training of the attack model. So we mimic the same retraining attack model here, and we continue training another generator based on the new attack model. And we keep chaining this, we keep going forward with this chaining process, and we see that at each stage, the perturbation patterns are diverging, which allows more random values to be explored in the state space. So any generator after the first stage is referred to as iPET Advanced in the talk from now. When we do a similar analysis of a retrained attacker, we see that the attacker no longer has any gain over no longer has a significant gain from their knowledge of the defense. So what caused this stochasticity between the instances now? We are also in principle training against different discriminators each time. So the decision boundaries that each generator is trying to fool are now different. So we head to the evaluations. We have evaluated our proposal using a real-world trace of 30 diverse IoT devices collected over 20 days. And we also use a synthetic data set which has a lot more traffic and 50 devices. So first we compare with the other schemes available in the literature, and we plot a CDF to show what percentage of devices were identified with a given F1 score. So an ideal defense would not allow any device to be identified with more than a random guess. And we see that iPET is the closest to the ideal curve here. And 42% being the maximum F1 score for any device to be identified, and 80% of the devices are identified with an F1 score of less than 20. We also try to highlight the bandwidth versus accuracy trade-off that we talked about earlier in the talk. And we see that while the existing approaches show a decreasing trend, they'll definitely converge sometime later, sometime in this graph with a low attack accuracy. But we see that iPET can achieve a much better defense or a much lower attack F1 score in this diagram at 40 times lower bandwidth, even just in this diagram as we see. We also demonstrate the transferability across not just different attack models, but also different defense parameters. To take an example, we consider that an attacker might be using a CNN-based attack model, and iPET would have considered a BILE-STM-based attack model to train its generator, and still the attacker can just get an F1 score of 7.07%. Finally, we also talk about a powerful adversary, more powerful than the retrained adversary we talked about. This adversary has access to several iPET instances. They also have white box access to the model architecture and the defense parameters. And we see that they achieve less than 50% attack accuracy in any case. So that's the best they can do, even when we give them all the strength and all the knowledge of the defense. So in conclusion, iPET is a generative attack adversarial perturbation defense for IoT to secure IoT communications. And we have shown that the defense generalizes well across different attack models. Thank you. I'll take questions now.
Thank you for the presentation. So we have one question from, I think it's a two-part question from Mehdi. I think the first question is there some kind of a latency impact of your model, or is there some consideration for latency when you are doing this, making this model?
So this is a generative model, and how that helps is you can, and it's agnostic of the traffic, something I did not highlight during the talk. So it's agnostic of the live traffic. You can just pre-generate all the perturbations, and that really helps you reduce the latency by a lot. We do shadow simulations, and we see that we have an additional latency of around 100 microseconds, which is pretty tolerable. But the generative modeling that we undertake really helps us reduce the latency by a lot.
Okay, we have other questions as well. So there's a question from Ryan. What features is the LSTM using when distinguishing the constant rate traffic on the main result slide?
So the LSTM-based attack is more of the time series based attack that we initially talked about. And it's using the packet count and the packet length in both directions. So we do not consider any protocol-specific features which we know can be easily obfuscated. And this is also the state-of-the-art attack that is proposed in the literature.
Okay, and I think we can take one more question from Stephanie. So in the figure on slide 28, the related work seems to decrease with excess bandwidth, but iPET does not. Why is that?
That's a good question. So we tried to analyze that, and you can see the paper for more results. And we see more often than not, iPET reduces the attack accuracy and then pretty much stabilizes. So from our analysis, we could see that that's pretty much the best that we can do. Beyond that, even if you give it more bandwidth to play with, it does not really help you a lot. So it does come down. So if I go towards the left of this graph, you'll definitely see iPET going up. But after a point, it just stabilizes. It doesn't go down any further.
Thank you so much for the talk.
Thank
Let's
you.
thank the speaker. And